find the chat box. Just a moment. Okay. So H. Raghuram, right? That's the name of the student. So what is the similarity between signals and systems or any signal processing concept and control systems? So that is the first question. So first question is, what is similarity between signals and systems or any other signal processing concept and control systems? So control systems essentially involves getting physical systems to do your bidding, or in other words, track some references of your choice, or to reject unwanted signals, which are called disturbances, and so on. Now, this process of getting signals to be tracked or disturbances to be rejected can be done by modeling the physical system either in the time domain or in the frequency domain. And if you do modeling in the time domain, you have a certain set of tools called state space based design and control, which can be used. If you are modeling the system, however, in the frequency domain, then you discover lots of similarities in the way you model the system and the control system, in the way you model a physical system when you are doing control, and the way you model a physical system when you are studying signals and systems course. Okay. So, for example, you use Fourier transforms, you use Laplace transforms, and so on. And this, and in terms of specifying the disturbances and the references, we talk about the frequency content or the frequency spectrum of the disturbances and the references and so on. So this is where the commonality in tools comes about. I don't know what else is contained in the signals and systems course, but if signals and systems also looks at time domain response of physical systems, then state space based techniques also therefore would overlap with what is taught in signals and systems. So the tools are the same. The tools used for modeling of a physical system are the same, but signals and systems are more, I assume, for analyzing a system and understanding its behavior or modeling a system. Whereas in controls, the same mathematical tools are used for getting that system to do what you want it to do. And when you have to get that system to do what you want it to do, you have to deal with issues of stability also. That's the extra feature that you would need to worry about when you are trying to do controls. I hope that partially answers the question that was asked. So there are lots of similarities from the viewpoint of modeling, but from the viewpoint of the goals of a signals and systems course versus or signal processing course versus a control system course, there are big differences. So that's the first answer. And the second question is, give some tips to learn tough concepts of control systems for a student having some prerequisites of signal system or signal processing. So I don't know what you mean by tough concepts of control systems. There are a few concepts in control systems which are important, and I wouldn't call them necessarily tough. These concepts include, for example, the notion of Nyquist stability theory, and then there are tools for design such as Bode plots and root locus and things of that kind, all of which are useful if you adopt a frequency domain based approach for modeling a physical system and then implementing your control. So those concepts are discussed in my course and are also available as part of are also widely discussed in undergraduate textbooks devoted to feedback control. For example, the popular one written by Professor K. Ogata. Okay, so I don't know what tough concepts you are referring to, but these are the concepts that are important for analysis and control of feedback systems, of control systems, and Nyquist plots and Bode plots, Nyquist stability theory, and so on. And they're available in these books and also in the lectures. So the third question is, suggest some books that give both theoretical and practical concept and also some numericals to practice. So I think most textbooks on controls discuss theory. I don't want to mention any specific book because control systems, by their very nature, are cross-disciplinary, by which I mean that the central concepts of control systems can be applied to any physical system, which could be of interest to a chemical engineer or a mechanical engineer or a electrical engineer. So if we have to discuss some things that might be of use to every one of these extremely disparate and different engineering disciplines, we have to agree on a common language, and that common language is that of mathematics. Okay, so all control systems textbooks by default, use mathematics and discuss transfer functions and Laplace transforms and such things. So every textbook that you can Google and look up would have theoretical concepts in relation to feedback control. Now, many of these textbooks also come with numerical examples for practice. So I mentioned one textbook by Professor K. Ogata. Then there are other books. I don't remember the names now. There's one called Feedback Control of Dynamic Systems by Gene Franklin, G.F. Franklin, Abbas Emami Naini, and David J. Powell. So this is yet another fairly popular textbook on controls, which involves numericals also. And then there is one more textbook which whose name escapes me right now. I can look it up and then I can request the TAs to post it on the forum sometime later. All these books discuss both theoretical concepts as well as numericals. And they also discuss certain specific practical examples. Okay, so you have servo motors, for example, that are discussed. You have some industrial applications of control that are discussed in these books. So they give a fairly broad overview of control with both theoretical concepts, practical concepts, as well as numericals. But they will be more theory heavy. Okay, practical concepts are limited only to illustrating some theoretical concepts, because, as I said, these theoretical concepts should be of use to a variety of engineering disciplines, and they don't want it to be restricted to a specific discipline. So that is my answer to the third question. So I could think of two books. There's a third. I don't know if I have shared lecture notes or not, but it's possible that I have also provided some reference books for this course on the NPTEL website, and those other additional references can also be used, and they will contain nearly all of them will contain all of these three types of discussions: theoretical, practical, and numericals. So that's my answer to the question that was asked in the chat box. Any other question that you guys have? Okay. So does the person who asked this question have any further, ask these three questions, have any further clarifications to request?
They have also posted a few other questions on the chat box.
Okay. Siddhant Kulkarni, what is the difference between control design in frequency domain versus time domain? And what is the difference between optimal control, LQR controller, and controller we are learning in this course? And when to use which? It's a very relevant and important question. Unfortunately, there is way too much detail here. So what is the difference between control design in frequency domain versus time domain? The difference is that the physical system that you want to control is modeled in the time domain through differential equations in one case, and in a frequency domain based control, it is modeled in the frequency domain through transfer functions. And you again use transfer functions for controllers, and you use state space based control techniques in time domain. So that's the difference. So you take the Laplace transform and of the physical system, define a transfer function and use it for design, for frequency domain based design. In time domain, you just deal with differential equations. So at the level of, at that basic level, that's the difference. Otherwise, as far as you are dealing with the linear physical systems, the results will be the same. So whether you use frequency domain based design techniques or whether you use time domain based design techniques, you should be able to get the same kind of performance regardless of which control design technique you use, okay, which domain you model your system in. So what is possible in time domain is also possible in frequency domain and vice versa. That said, from the viewpoint of intuitiveness, from the viewpoint of ease of understanding, I am of the view that frequency domain is superior because it converts convolution integrals into products and therefore is more intuitive and easy to use. But time domain is better in the sense that it can also be applied for nonlinear systems. So for linear systems, either one is fine and both will give you equivalent results. But from the viewpoint of intuition, frequency domain is preferred. For nonlinear systems, you can't work in the frequency domain because some of the theorems that are necessary to go from time domain to frequency domain are not applicable for nonlinear systems. So you have to work only in the time domain. So that is the power of time domain. If you are having a nonlinear system and you want to implement a nonlinear control system, time domain is the way to go. What is the difference between optimal control, LQR controller, and controller we are learning in this course? So LQR controller is a type of controller that emerges from optimal control. So optimal control's goal is to implement control in such a way that some cost function is optimized. This originated during the space race between Soviet Union and United States in the 1970s and 1980s, where if you want to execute if you want to maneuver something in space, you have to be very mindful of the amount of fuel that you are going to be consuming or the amount of electricity you are going to be consuming. So therefore, when you execute something, you want to be sure that you execute it with minimal consumption of fuel or electricity or whatever. That was the origin of optimal control. Okay. Now, LQR controller is a type of controller whose control output emerges from minimizing a certain quadratic functional of states and in control effort. Okay, so LQR controller is applicable typically for a to control a linear physical system, and that cost functional that you define would be a quadratic function. That's why the Q in the LQR comes about. It's a quadratic function of the states and the input. So it will be of the kind X transpose QX plus R transpose plus U transpose RU, where U is the input you provide to the plant and X is the state variable of the plant. Okay, so it's LQR therefore is a subset of optimal control. Okay, so both of them find a way to optimize some functional during the time that you are implementing control. Okay, and LQR need not necessarily optimize fuel or any such thing. You can come up with more general cost functionals, and you can tune the weightage that you give to the states, the error in the states and the control effort and so on, depending on your requirements, and then you obtain the control effort. This has to be done, however, using a computer, because this involves solving matrix equations or sometimes matrix differential equations called dynamic Riccati equations or matrix Riccati equations. So that's what optimal control is all about. It's about moving from one point to another or controlling a variable in such a way that some cost is minimized. Okay, the control that we are learning in this course is a linear controller which does not try to optimize some sort of cost like fuel or some such thing. The controller that we are designing is intended to achieve certain transient response specifications, some robust tracking specifications, or disturbance rejection specifications. Okay, they might not end up optimizing fuel, they might not end up optimizing any particular cost function, but they help you achieve the desired transient response and the desired extent of rejection of disturbances and tracking of references. So that's what is the difference between the kind of controllers we discuss in this course and the kind of controllers that optimal control deals with. Optimal control generally requires you to use computers for calculating the control effort and are less intuitive. The kind of controllers that we discuss are designed by us, sometimes by hand, and therefore they're very intuitive and you know exactly why you have designed the controller in the manner that you have. Okay. Can you please tell us some insights on how to realize controllers physically? Yes.
So Siddhant Kulkarni here. The previous
yes,
question.
Please continue. Yes.
So it's like what I understood is we are designing our controller considering some dominant pole here.
Yes.
In our controller. So is it like when we apply a optimal control where we use state space approach, we are trying to control more than one poles of our system and simultaneously?
Correct. You are trying to place, that's not optimal control per se, that's called pole placement in state space, that you are trying to place all the poles of your closed loop system. Yes.
Okay. And so like, is the optimal control may not be robust sometime, or we can design it
Definitely.
using...
Can we make optimal control robust? I'm not very sure about that. I think there has been a lot of literature pointing out that optimal control can sometimes not be robust, in the sense that if you don't know the plant's model very well, what you think is the output might not be optimal. So that is there. Whether that issue has been addressed adequately or not, I'm not sure. But when you have robustness issues, the linear control technique that we are talking about is one straightforward way to deal with it. There is yet another control strategy called adaptive control, which also gives you robustness.
Okay. Thank you, sir.
Yeah. So the next question is, can you please tell us some insights on how to realize the controllers physically? What are the main challenges that we face while doing this? So over the past several decades, controllers have been realized physically using several different techniques. To start with, before electronics became widely adopted, people used to use pneumatic systems and hydraulic systems to realize controllers, like PID controllers and such things were realized using pneumatic and hydraulic elements. And since they were realized using such hardware, the scope of the kind of control loss that you could realize was also limited. You couldn't come up with any control law that you could think of and realize it using a pneumatic or a hydraulic system. Then, with the development of electronics, people started to realize these controllers using operational amplifiers. That became a lot more flexible because now you have these linear devices with which you could realize easily inverting amplifiers, non-inverting amplifiers, differentiators, integrators, and so on and so forth, band pass filters and all of that. So that was the advantage. And after that, with the development of computers, many of these controllers are now realized in a computer. Okay, and that brought in even more flexibility because certain nonlinear control schemes, which are very difficult to implement with op-amps and so on, can be easily realized using nonlinear control, using computers. So that's how you realize, these controllers. Please give us a little demo of how to use Simulink to analyze transient response and steady state response. I think this is a question that my students might be able to, my TAs will probably attempt to answer. Please explain more how a Bode plot can give us approximate location of the closed loop dominant pole with information of the gain crossover frequency and the phase margin. So this has to do with Nyquist stability theory. So when your Nyquist plot is very close to the critical point, which is -1 plus J0, then your closed loop poles will be very close to the imaginary axis. On the basis of that, you conclude that for small phase margins, your closed loop poles will still be close to the imaginary axis, and you can estimate the location approximately, from the gain crossover frequency and the phase margin. This is about as much as I can think of now. There are other ways to look at this also. You can come up with an approximate second order model for your closed loop system and match that with the corresponding transfer function for the open loop system and show that the closed loop poles of that second order system will be approximately determined by the gain crossover frequency and the phase margin. That's another way to do it. Since controllers give output to actuators in practice, do we combine actuators and plant dynamics and design controllers? Yes, we do. Correct. Fifth, when we are using dominant poles method, introducing a zero at low frequency and a pole far location, will there be any difficulties in realizing it? Yes, definitely. Having a pole farther away will require you to have greater bandwidth for your controller. So you have to therefore do the trade-off when you're implementing it in practice. In practical plant with feedback, we use sensors to measure output and measure output and feed it to the input side. There would be some delay associated with it. How do we deal with it in practical applications? Delay is a very important contributor. We will be discussing delay and its effects later on in this course if it has not been done yet. So you please wait for a few more lectures and you will understand the effects of delay on feedback. So we have then Gifty Benjamin, physical interpretation of poles and zeros. So physical interpretation of poles and zeros, it's when I take the Laplace inverse of a system's free response to certain initial conditions, the system usually decays to zero exponentially, and the rate of decay down to zero are characterized by the magnitudes of the poles of the physical system. And the zeros determine the proportion in which these different poles are combined to give you the physical system. That's the best that I can do to provide physical interpretation. So you can look at the time domain response of a physical system, and then from that infer that its response will be fast if it has fast poles, and will be slow. They'll all be exponentials. There'll be fast decaying exponentials if the poles are large. There'll be slow decaying exponentials if the poles are small. And if the poles are unstable, then you will have increasing exponentials. Best tool among Bode, Root Locus, and Nyquist to do control design. Between Bode and Nyquist, it is very clear. Bode is a much better tool for doing control design. Between Root Locus and Bode, Root Locus is useful for looking at closed loop closed loop poles. I have talked about in the course, I talk about how a control engineer has two goals. One is performance engineering. The second is stability engineering. For the purposes of stability engineering, Root Locus is better. For the purpose of performance engineering, Bode plots are better. However, all said and done, it is the Bode plots that help you deal with rejecting disturbances, tracking references in a systematic manner, and at the same time, through the notions of phase margin and gain margin, guarantee you stability. So between the three, Bode plots are the best, followed by Root Locus. Once you are done with the design using Bode plots, for analysis of the closed loop poles, I would recommend Root Locus. Nyquist plots are not as powerful as either of these, so they are not really good for control design, but they are very useful for determining stability of a feedback system. They are the only way you can determine stability of a feedback system when you are dealing with systems with multiple non-minimum phase zeros and unstable poles and things of that kind, and the Bode plots do not make sense. Then you have to go to Nyquist plots and look at applies Nyquist stability criterion properly to get the stability. Okay, so one advantage of okay, all right. So I think these are the questions that are there right now. I think I will stop at this point, and I will let Dr. Lavanya, Mr. Krishna, and Mr. Sagnik take over from this point. Thank you very much. I shall exit the meeting now. Lavanya, can you please go ahead?
Yes, sir.
Yeah.
So I'll just share my PowerPoint slide to solve the questions. Okay. Please open the. PowerPoint, Krishna.
Okay. So we are trying to share the screen. Participant. So,
How do we share?
so I'm not participating.
Can the NPTEL office kindly allow sharing of the screen to Krishna KR1 desktop? This will be problem.
You only can share
Only I can share.
your post.
On post? Oh, okay, okay.
Uh,
Sorry, your question.
so we'll start with assignment 1. So, Lavanya will be discussing first question. I'll talk about the second question. So we'll try to give a. So if we see the, I am unable to share the screen. So what I'll try to do is I'll post the question. Okay. I'm trying to share my screen to project this these questions of the assignment 1. So in question 2, we have asked what type of systems does not follow differential. Actually, we asked what kind of differential equation is the given equation. So I think I don't know how to.
Hello, Krishna.
Yes, Lavanya. Okay, you are able to share this.
Yes, Krishna. I think through my link I can share the screen. So you may want to come over to this room. Until then, I'll start explaining the questions. So some of the assignment 1 questions. Okay, I hope my screen is visible to everybody. All right. Okay, let's see how to try this on. So the first question in our assignment was basically to check whether our system was it a linear system, and we had to check for the time invariance. So in order to check the linearity of our system, we had to in order to check the linearity, we need to check for 2 conditions. One of the condition is to check for the superposition property. The other condition is to check the scaling property. And how do I make this disappear? Okay, just a minute, people. I'm unable to view the question, so I'll just drag it a bit down. All right, thank you. Yeah. So the 2 conditions were the 2 conditions were the superposition property and the scaling property. Now let us look at the kind of signal that we have received, which is a product of linear operator L1 of u times L2 of u. So we know someone's calling me. Okay, so we know that a product operator or a multiplication operation is non-linear in nature because it does not it neither adheres to the superposition nor it adheres to the scaling. Since both of them are not satisfied, we know that the system is non-linear. The second check we have to do is for the time variance. So what is time variance? The time variance, a time invariant system is the one if we shift our, let's say we have our input signal u of t, and if we shift our input signal by an amount t minus t naught, then our, let's say if our output is x of t, it should also shift by the amount t minus t naught, which means that any shift in the input will not will result in the corresponding shift in the output. But since our output is also a function of the time variable t, we can say that shift in t minus t naught will not result in an identical output shift. Hence, the system is non-linear time variant system. Okay, for the
Share the website. Please.
oh, share the website, sure. Let me directly go to the website. For the second question, my friend Krishna would be discussing.
So for the second question, we can apply the superposition and scaling principles here. But before doing that, we can actually just try to arrange this differential equation into a standard form where we can actually try to verify whether there are terms which are multiplied. Like here, differentially in this ODE, the x is a dependent variable and t is a independent variable, and t can be like a forcing. T is a independent variable. So I'll try to. Uh, so I think we can just print all the. So as we can see, this differential equation, we can try to. There are some technical issues. Okay. So we can try to rearrange this equation like into standard form, like d square plus 3 into dx by dt plus t cube, and we can just multiply this whole thing by the x, because in the last term x was in denominator. If we multiply
we'll get into some standard form where we can notice that the derivatives of the dependent variable and uh, are multiplied with variable dependent variable, and this gives rise to a classification of nonlinear system. So this is not a nonlinear system, that much we are sure. And so we have to look for the option where the nonlinearity is there. And one thing we can do is we can actually uh, so square into x plus 3x into dx by dt plus t cube we will be having, and we can take t cube to the other side, and this becomes like a forcing function. Then we can say that this is not homogeneous again, so then it will be inhomogeneous function. So in that way we can see that it's non-linear and inhomogeneous. And also the coefficient, if we observe, there are these coefficients of the left hand side doesn't have any time varying terms, so that's why we classify it as a time invariant system. So these three in combination will give us the option, right option, like inhomogeneous non-linear time invariant system. So this is the second question. And for the third question, uh, uh, so to solve this question, we have to use a initial conditions based solutions. We The technique that is discussed in the lecture is using Van der Waals matrix, where we have a matrix relating initial conditions to a characteristic. So we have to start with, we assume that there is a uh, um, general solution of e power lambda t, and then when we assumed the solution, we uh, substitute in this differential equation and solve for it, we'll get a equation solution of the form, general form, uh, like uh, like lambda 1 t plus c2 lambda 2 lambda 2t. So sorry for the writing, there was some distortion. Um, then in lecture it will be discussed that there will be a relationship between the initial conditions, because if you have two unknowns in these equations, we have to find this, we at least need two initial conditions, that is x of 0 or x dot of 0 or x dash of 0. This will place in this matrix, and then so this will be related to a matrix of this form, which was discussed in a lecture. And But to obtain a unit impulse response, our forcing function is unit impulse with magnitude 1. When we in that case, when we match the singularities, then we will get a initial conditions as 0, 0 plus 1 and equated to 1, 1, lambda 1 and lambda 2. And those will be related to C1 and C2. And if we solve this and find lambda 1 by just substituting in this equation, we'll get a characteristic equation of lambda square is equals to 9 lambda plus 18, which equal to 0, and then we'll get lambda 1 is equals to minus 3 and lambda 2 is equals to minus 6. And if we solve this equation, you will get C1 and C2 as a 1 by 3 and minus 1 by 3. Thus the solution impulse response, the solution that we get, we call it as impulse response, and that is indicated by G of t, which is given by 1 by 3 e power minus 3t minus 1 by 3 e power minus 6t. So which is the option, this option. So which is which we can see there. So next question we have. So Lavanya will be discussing next question.
Thank you, Krishna. Let me just check the portal if someone has any questions. If you people have any questions, kindly unmute yourself and ask us. Okay, there are no questions. Okay, so the next question is that it's given that if the impulse response of our system is given by a certain function g of t, then we have to identify what is the response of our system to input comprising of an impulse input and a shifted impulse input. So here in this question, we are basically checking the concept. We basically use the concept of or the property of linear systems. Since the system is linear, if the impulse response of a let me just draw if my okay. So let's say if u of t is the input to our system and x of t is the output of our system. If we would give delta of t input, then the response of our system is g of t. If we give if we give shifted delta of input, which is delta of t minus t1, then the output of our response will be g of t minus t1, because the system is still linear time invariant. So if our input u of t is difference of delta of t minus t1, then our output will be g of t minus t1. So if we solve this, I think we would get our if we solve this, I think we would get our response as 4a, this one. All right. Going to the next question. I'll first drag it down. Okay. So the next question is here that the unit step response of our system is this much. Then what is the impulse response of our system? So again, let us take into account that we have this system whose second order differential equation we do not know. If u of t is the input and x of t is the output of our system, they have given that if u of t is a step input, then our output is given by the expression shown above. But what is the relationship? Let us take a look at, in order to solve this question, we take we take into information that the step input is nothing but its step input can be represented in terms of an integral of an impulse input. So step is nothing but an integral of an impulse input. So if I need the impulse input from the step inputs, of t would be nothing but a differential of the step input. So instead of u of t, if I were to apply the impulse input of the system, then the output in, so since delta of t is nothing but a differential of the input, then the response to this delta of t will be the differential to the response of the x of t. Oops. Which is in this case corresponds to option B. All right. Jumping to the sixth. Okay. We'll just do the sixth question in the end. We'll jump to the seventh question. So in the seventh question, we have asked, like, what is the Fourier transform for signal which is given by 1 plus e raised to minus at for time greater than 0 and 0 for t less than 0. So in order to solve this question, we can split this input u of t into two input signals, u1 of t and u2 of t, where u1 of t would be our unit step input, where we get signal only for t greater than or equal to 0, and u2 of t would be our exponential input. So we know that by from the definition of the Fourier transform, we know that the Fourier transform is defined as integral from minus infinity to infinity u of t e raised to minus j omega t dt. So here, if you would substitute u of t for the unit step input and for the exponential input, we would get, for the unit step input, we would get the Fourier transform. So u for unit step, if we do a Fourier transform, our response would be 1 by j omega, which is a constant, plus pi times delta of omega. While for e raised to minus at, if we do a Fourier transform, I think we would get 1 divided by a plus j omega. So now if we would add these two and simplify the expressions, our result would look something which is A, B, C, and D. Yeah, our result would look something like this. Okay, so for the sixth question, my lab mate, the other T. Krishna will take care.
Okay. Hello again. This is the sixth question. I have pasted it with some other serial number, but it's the sixth question. So basically here we are trying to ask you the understanding of Fourier series. So the Fourier series is like we can try to represent any arbitrary periodic signal in terms of sinusoids and cosines. So this is basically reconstructing the signal in terms of the known base signals like sines and cosines. The standard form is given here, and I have asked you, we have asked you to find one of the coefficient. So that is A8, which is a coefficient of sine. So to find this any general coefficient AR, that is AK here. So which is given by 1 by 2 by t into some t naught 2 t naught plus capital T into the function that is given as a u of t, which is graphically shown here, and into sine 2 pi k t by capital T into dt. So this is the integral you have to evaluate in order to answer this question, that is A8. So here instead of k you can use 8, but here we can use the property of the this integral, because sine, if we look at the sine, it will be it is odd function. And the function that we have given in the question is an even function. Now, if we multiply, let's say, any even function, for example, the one that is given here, if we multiply both of them, we'll get a product which will be like symmetric on both the positive and negative side. That means it will have a area, equal area on both the positive and negative sides. Thus, the total integral over the time period capital T, which is this, from 0 or this t by 2 to t by 2, anything you can take and do integral. This will cancel out and you'll get a 0. So here we are basically using the property of even and odd functions and their multiplication to find the coefficient. So thus the answer will be 0, because this science doesn't any science won't make this signal. Next, I'll stop here, and we'll be our friend Sagnik will be discussing other few questions.
Okay, so for questions 8 and 9, actually, there are some small typos in the question. So I meant to give an s minus 5 here, but ended up writing an s plus 5. And the form of the ramp function in question 9 is incorrect. So we have already contacted NPTEL office about this, and they will ensure that you get credit, or these questions will not be counted towards the assignment. As for question number 10, we'll discuss this. Yeah. So in question 10, we have a transfer function which is given by, where is my mouse? Yeah. So in question 10, we have a transfer function which is given by this, right? And we have been said a ramp input is applied at t equal to 0. So find the output x as t approaches infinity. So this is a question which is based on the concept of the final value theorem. Okay. Right. So what you have to do is to find the output x of t as t approaches infinity, we know that. Second. Yeah.
Share this screen. Share this screen. Oh, that screen.
Okay. Just give me a second. The screen.
Maybe you
Just
can
start
directly
start sharing here.
sharing here.
Okay.
Screen, total screen.
Okay. Okay. So yeah, as I was saying, there's a question in final value theorem, right? And you've been given this transfer function. You have to find the output x of t as t approaches infinity. So in order to find this, we know that if you want to find the given this transfer function, if we want to find the output, how do I use the eraser? You can't? Okay. Okay, never mind. So if you want to find the output x of t as t approaches infinity, this is the same as finding the value of the transfer function as s approaches 0. S this is the same as finding the limit of the transfer function s times g of s as s approaches 0, right? So we have this form of g of s. So as you have to find the limit as s approaches 0 of s times this entire expression over here, right? So this will be by 10 s cube plus 61 s square plus 78 s plus 27, right? So if you want to find the transfer function for this, this will be a 1 by s. I'm very sorry. So the s's will cancel out here, and the final value which you obtain will be if you place the value of s equal to 0 for all of these, you will get this limit to be equal to 18 by 27, right? Which is just equal to 2 by 3. So which is the solution to this problem, right? So it's the third option. Well, no problem. So basically the solution to this problem is this one, right? Yeah, the solution is option C, right? So this completes assignment 1. Now we'll move to the questions in assignment 2. It's
Excuse me, sir.
Yes.
This is Navin from NPTEL, and I have put your direct message. Could you please check that?
Sorry, what did you ask? Could you please
I,
repeat the
I have
question?
sent you a message in the chat box. Can you please check that?
Okay, just let me. Actually, I can't see your message. Someone has posted a message in the chat box, but I can't see it here. These were questions which were given directly, like previously. Did they post it as a...
Can someone read out the questions?
Can someone, whoever has posted the question, can you please read it out once? Because we can't see it.
So this live session is about 4 to 5 only.
Okay. Yeah.
Gentle reminder.
So
Yes.
yeah. So yeah. So for to the students, so the time for the live session is actually up for us. So we'll discuss assignment 2 in the next session, which will take place next week. Okay. Yeah. Thank you so much.